Okay, so after studying the Norton equivalent circuit and the Thevenin equivalent circuits, now it's the time to study the maximum power transfer from source to a load. So let's consider we have some resistive network, and that resistive network is containing the independent and dependent voltage and current sources, and it is delivering a power to a load. So this network can be just transformed into equivalent Thevenin voltage source and a Thevenin resistance. So definitely during this transformation we are interested to transform the maximum power to the load, and it's very practical trait because for example, if you consider the power system is consists of the generation, transmission and distribution, and of course the main aim of the power system is to transform the maximum generated power to the load. Same is the case with the communication signals. When you communicate with some, and if you transmit some signal from source to a load side, so of course you will be definitely interested to transform the maximum power, and definitely you will be interested to get the maximum power at the load which has been transmitted from the source. So this is really a practical case. So let's consider a circuit, and we have the Thevenin voltage and Thevenin resistance, and this has been obtained from this resistor network, and this is connected to a load resistance RL. Let's assume that the current is flowing in this network is I. So the power dissipated in this load is equal to I square RL. So I can be computed from this relation, that VTH divided by RTH plus RL, because RTH and RL, they are connected in series. So you have this relation for the current. Substituting this relation over here, so you have VTH RTH plus RL whole square into RL. Taking this VTH square out, you have RL divided by RTH plus RL whole square. So when you want to compute the maximum power, you have to differentiate this relation with respect to RL. So you can differentiate this dP by dRL is equal to VTH is independent of RL, just taking this as out, and taking the square of the numerator. So if you just take the square of the numerator, it will be 4. So this is 4, okay, and writing the denominator as here, and differentiate this with respect to RL. So dRL by dRL is unity, so you can simply write 1 minus, write the denominator, the numerator, and differentiate the numerator. So this numerator is containing RL, it has a square sign, so you can just use the rule that RTH plus RL multiplied by 2 into dRL by dRL, which is equal to 1. So you have this relation. So rearranging this expression, we have TH whole square, taking RTH plus RL is common, RTH plus RL is common. So you have RTH plus RL plus RL and minus 2 times RL divided by RTH plus RL 4. Okay. So, and making this as 0. So if you just substitute this as 0, this portion will go to 0, and you will have just to substitute this as equal to 0. Then this will ensure that this RTH plus RL minus 2RL, if this is 0, then this will ensure that this dP by dRL is equal to 0. So it is RTH plus RL minus 2RL, so RTH minus RL. So RTH minus RL equal to 0 will ensure that dP by dRL will be equal to 0. So this implies that we have RTH is equal to RL. Interesting result. So if we have the load resistance equivalent to the Thevenin resistance, then we will ensure the maximum power transfer. So simply substituting this in the relation for power, which we have just written. So I simply remove all this, and we have the relation for power is equal to VTH square RL and RL plus RTH whole square. So substituting RL is equal to RTH. So RTH and RTH square RTH, and here you have 2 RTH square. So we have now VTH square RTH will cancel with this 1 RTH, so you will have 4 times RTH. So this is the relation for the maximum power. On the other hand, if you substitute RTH is equal to RL, you will have this relation is equal to VTH whole square divided by 4 times RL. So this will be the maximum power which can be transformed to the load when you consider RL is equal to RTH. So just to explain this maximum power phenomena, we just saw a couple of examples on it, and hopefully this will be more clear with it. So we have this example. Okay? We have voltage source, resistances, and we are interested to transform maximum power to this load. First part of this question asks you to compute the value of RL so that results the maximum power transfer. And after that, we have to compute the maximum power which has to be transferred from this source to the load. And after finding this maximum power, we have to compute the percentage of the power, the maximum power. We have to compute the percentage of the power delivered to the load, transmitted from the source. Okay, so as a first step, we have to compute RL. So as I told you just a little while ago, that RL is nothing but equal to RTH. So if you have somehow able to, if you can compute RTH, then that RTH can be equal to RL for the maximum power transfer. So for this, we have to compute RTH, the Thevenin resistance. So this circuit, just mark these terminals A, B. So remove this RL, compute the Thevenin source, and compute the Thevenin resistance for this circuit. This is a very simple circuit, so we don't want to use no voltage method or mesh current method and so on and so forth. We just use the voltage divider rule. So using the voltage divider rule, you can compute the Thevenin voltage, which is equal to voltage at point AB. So this is equal to the total voltage multiplied by this 150 ohm resistance divided by 150 ohm plus 30. Okay, so we have 180, 360 divided by 180 will result 2 multiplied by 150, it will result 300 volt. So we have the Thevenin voltage is equal to 300 volt. Now the Thevenin resistance is that just make this as short circuit, compute the equivalent resistance. So the Thevenin resistance is equal to the parallel combination, the equivalent resistance of these parallel resistances. So 30 multiplied by 150 divided by 30 plus 150. So this is equal to 25 ohm. So the Thevenin voltage is 300 volt, the Thevenin resistance is 25 ohm, so it means that RL has to be adjusted as 25 ohm for a maximum power in order to have the maximum power at the load side. Okay, now the second part is we have to compute the maximum power. So this is part A. Now part B is the maximum power. Just recall the formula is equal to VTH whole square divided by 4 times RL R RTH. Okay, so we have to use this formula. So 300 square and 4 times RL, this is 25 ohm. So the maximum power is equal to 900 watt. Okay, so this is the maximum power received here. Okay, so now we are interested to have the maximum power delivered by this load, maximum power received by this load resistance, and the maximum power delivered by the source. So what percentage of power has been delivered to this load? So we have to first compute the power delivered by this, of course, the source. So let's assume that some current is flowing from this source. So this current into this voltage will result into the power delivered by this source. Okay, so we have, let's compute this. So how to compute this current? Let's denote this by IS, the source current. So this voltage minus this voltage divided by this current. So we have to compute this voltage. Okay, so VAB is the voltage. We have to compute this voltage. Okay, so how to compute the voltage? VAB. So VAB is equal to the Thevenin equivalent voltage, because this has been transformed into the Thevenin equivalent source. So let me first draw the Thevenin equivalent circuit so that this expression can be easily understood. So VAB is equal to total voltage 300 and 25 ohm resistance divided by 50 ohm, because 25 plus 25 is equal to 50 ohm. So VAB is equal to 150 volt. So now the voltage here is 150 volt. So now you can easily compute the current IS. So IS is equal to, here IS is equal to 360 volt minus, here voltage is 150 volt divided by 30 ohm resistance, which comes out to be 7 ampere. So now you can compute the power delivered by the source is equal to 360 and multiplied by 7 ampere, since it is delivering power, so we can represent this with negative sign, and which is equal to minus 25 20 watt. Okay, so now this is the total power delivered to the circuit, and the total power we got at the load side is equal to 900 watt. So let me write this as 900 watt here. Okay, so now you can easily compute the percentage of power which is delivered by the source. Percentage of delivered power is equal to total power at the load side 900 watt, total power delivered 2520 multiplied by 100, which is equal to 35.71%. 35.71% of the power delivered to the load. Okay, so this is how you have to compute the percentage of maximum power, or the maximum power which has been delivered to the load. So ideally, the whole power has to be transmitted, has to be delivered to the load, but this is not the case in practice. That's why you have to compute the percentage power. So we will solve another example in order to explain the maximum power more clearly.